Chapter 1.10.8 Dynamic Resource Allocation. Summary. Dynamic resource allocation in Kubernetes is an API for managing resources like GPUs in pods, similar to persistent volumes but for various resource types. Third-party drivers track resources, while Kubernetes handles allocation using structured parameters. Structured parameters allow Kubernetes to define requirements for various resources, with v1.30 introducing this feature. Resource allocation can also be managed by control plane controllers, allowing more driver-specific handling. Kubernetes version 1.31 features cluster-level API support for dynamic allocation but requires explicit enabling. Resource drivers must be installed, and API versions play a role in defining resources and claims for pods. Dynamic resource allocation. Core dynamic resource allocation with structured parameters was introduced in Kubernetes version 1.30 alpha. It allows requesting and sharing resources within pods using structured parameters. Dynamic resource allocation in Kubernetes version 1.26 introduces control plane controller support, enabling drivers to manage allocation with Kubernetes scheduler assistance. The Dynamic Resource Allocation API generalizes persistent volumes for devices like GPUs, with drivers tracking these resources. Allocation is managed via structured parameters. Before you begin, Kubernetes version 1.31 introduces new features for dynamic resource allocation but requires explicit enabling and installation of a resource driver. For previous versions, consult the Kubernetes documentation for applicable details. API. This code snippet defines a device class resource with a specific name and selector expression, a resource claim template for managing resources with specific requests, and a pod spec with containers that reference the resource claims defined by the resource claim template. The API group, resource.k8s.io/v1alpha3, offers several resource-related components. First, the resource claim is a way to request and allocate specific resources for cluster workloads, stating what is needed and tracking allocation. Then, the resource claim template provides specifications and metadata for these claims whenever a workload is deployed. Kubernetes uses these templates to automatically manage resource claims for pods. The device class is crucial as it defines the selection criteria and configurations for devices in the cluster. This is set by administrators when installing resource drivers, and each claim to a device must correspond to a device class. Additionally, pod scheduling context is an internal mechanism used by controllers for coordinating pod scheduling when allocating resources via resource claims. Resource slice is another element that shares resource availability details and supports allocation coordination. The resource driver developer can choose between controlling this themselves or letting Kubernetes handle it, depending on their needs for flexibility or autoscaling support. With structured parameters, autoscaling becomes possible but might not cover all needs. Pod spec, within core v1, includes a resource claims field to define the necessary resource claims for a pod. Entries here refer to either a direct resource claim or a resource claim template, affecting whether pods share instances or have individual ones. This enables shared management of allocated resources across pods, especially in deployments or stateful sets. The resources claims list determines which containers in a pod access specific resource instances, facilitating resource sharing among containers. An example provided showed how a fictional driver created two resource claim objects, and each container in a pod accessed one of these claims, emphasizing resource management and sharing. Scheduling. ***1. Dynamic resource allocation. Resource drivers manage dynamic resources in clusters to fulfill resource claim requirements, marking them allocated once reserved. 2. Resource claims and scheduling. When scheduling pods, the scheduler checks resource claims and creates a pod scheduling object to inform resource drivers of suitable nodes. 3. Driver communication. Resource drivers exclude unsuitable nodes, helping the scheduler choose the right one for the pod. The allocation finalizes when resources are confirmed on that node. 4. Pod resource reservation. Pod scheduling requires all resources to be allocated and reserved to prevent blockages and ensure efficient resource use. 5. Structured parameters and devices. When using structured parameters, schedulers handle resource claim allocations with resource slice data and cell expressions to select devices. 6. Efficient scheduling. Using stored resource claim allocations, the scheduler makes faster decisions, avoiding driver communication, efficiently scheduling multiple pods. Monitoring resources. The kubelet offers a gRPC service to discover dynamic resources in running pods. For details on gRPC endpoints, refer to resource allocation reporting. Pre-scheduled pods. The code defines a pod named pod with cats, with a nodeSelector field specifying that the pod should be scheduled on a node with the host name of the intended node. This configuration ensures that the pod is pre-scheduled to run on a specific node based on the node's host name. When a pod is created with the node name specified, it bypasses the scheduler. If necessary resources aren't allocated, the kubelet can't run the pod, but will try again as conditions may change. This situation can occur if dynamic resource allocation is disabled or during configuration discrepancies. The Kube Controller Manager attempts to resolve this by triggering resource allocation. Using node name can block resources on a node. Instead, use a node selector to ensure the pod goes through normal scheduling or unset node name if possible. Enabling dynamic resource allocation. This code snippet uses kubectl to retrieve a list of available device classes in the Kubernetes cluster. By running this command, you can view the predefined selection criteria for certain devices and their configurations set by the cluster administrator. The code is using the kubectl getDeviceClasses command to retrieve information about device classes in Kubernetes. However, the output indicates that no resources were found, suggesting that there are no device classes currently configured or available in the cluster. This error message indicates that the Kubernetes server does not recognize or have the resource type, device classes, available. The command, kubectl getDeviceClasses, was run to retrieve information about device classes, but the server does not have this specific resource type defined. Dynamic resource allocation is an alpha feature that requires enabling both the dynamic resource allocation feature gate and the resource.k8s.io/v1 alpha 3 API group. Ensure Kube Scheduler, Kube Controller Manager, and kubelet have the feature gate. Use Kube AppServer parameters for details. A quick check involves listing device class objects. If your cluster supports dynamic resource allocation, you'll see device class objects listed. Missing features result in an error. When using a control plane controller, enable DRA control plane controller and dynamic resource allocation feature gates. Supported control is indicated by creating resource claims with a specified spec, controller field. If DRA control plane controller is off, resource claims controller field clears on storage. The Kube Scheduler's default setup activates the Dynamic Resources plugin if the feature gate is enabled with the V1 Configuration API. Custom configurations might need updates to integrate this feature. Beyond enabling features within the Kubernetes cluster, a resource driver installation is necessary. Refer to the specific driver's documentation for installation guidance, ensuring proper setup and functionality of dynamic resource allocation.